Hello friends, I welcome you all to my channel. Now today let us discuss about haloalkanes, the chemical reactions that haloalkanes undergo and their chemical properties. Actually, if we consider then haloalkanes, or we can say them as alkyl halides, are very reactive in nature, and normally they undergo four type of chemical reactions. The first one is nucleophilic substitution reaction, nucleophilic substitution reaction. Second, elimination reaction. And third, reaction with metals, reaction with metals like sodium and magnesium. And fourth, reduction. So these are the four reactions that haloalkanes very readily undergo, and all of these fours they very readily undergo nucleophilic substitution reactions. They very readily give nucleophilic substitution reaction and form a lot of products. Now since haloalkanes are very reactive, they are considered as synthetic tools in the hands of the scientist because they can be used to make a lot of products, or we can say that a lot of products are synthesized by using haloalkanes, and haloalkanes are very readily undergo nucleophilic substitution reactions. Now let us understand the reason why haloalkanes very readily undergo nucleophilic substitution reactions, what are the reasons and what are the probable causes for that. So as I have told you that haloalkanes are or alkyl halides are very reactive in nature, and this is due to the reason reactivity of haloalkanes. Reason behind that is, number one is polar nature of the compound. Polar nature of the compound. If we go ahead, then the general formula for haloalkanes is Rx, where X is a halogen atom, that may be fluorine, chlorine, bromine, or iodine. Any one of them may be there in place of X, or we can write it like this: and X. The halogen atom attached here is more electronegative as compared to the carbon atom. Electronegativity, so we can define the electronegativity as the tendency of an atom to attract the shared pair of electron towards itself is called electronegativity of that atom. So since halogens are more electronegative in comparison to carbon, halogen are more electronegative than carbon. So this halogen atom attracts the shared pair of electron towards itself and acquires a slight negative charge, and consequently a slight positive charge develops at the carbon, and this creates a center for nucleophilic attack, and this creates a center for nucleophilic attack. So now since a positive charge develops at the carbon, so now it is a suitable site for the nucleophile to attack. That's why alkyl halides are very reactive in nature and very readily they undergo nucleophilic substitution reaction. Now what a nucleophilic substitution reaction is? Next question that arises in our mind is that what a nucleophilic substitution reaction is. So we can say that replacement of a weaker nucleophile by a stronger one. Replacement of a weaker nucleophile by a stronger nucleophile is called as nucleophilic substitution reaction. Now next thing is, what is nucleophile? What is nucleophile? So nucleophiles are electron rich species. Electron rich groups that may have a negative charge or may have a lone pair. So either it may be negatively charged like OH minus or Cn minus, or have at least a lone pair of electron like NH3, in which there is a lone pair of electron at nitrogen. So such species which are rich in electron are called as nucleophiles, and since these species are rich in electron or negatively charged, so they are always in search of some positively charged site like this to attack or to bond with. Now, in case of halogens, if we consider the reactivity of alkyl halides towards nucleophilic substitution, reactivity order of alkyl halides towards nucleophilic substitution reaction. So since halogens are very good living groups and among them the iodide is best living group, then Br, then Cl. So reactivity order will be Ri will be more reactive in comparison to RBr, in comparison to RCl. This is the actual reactivity order of alkyl halides towards nucleophilic substitution reaction. Iodoalkanes are more reactive than bromoalkanes, then chloroalkanes. Fluoroalkanes readily do not undergo these reactions as the bond dissociation enthalpy is very high. For fluoroalkanes, the bond dissociation energy is very high due to the small size of the fluorine. So, under ordinary conditions, they do not take part or they do not undergo nucleophilic substitution reactions. Now there is an anomalous thing if we consider, then that is if we consider about the electronegativity, as we have discussed that they are very reactive. And why they are very reactive? They are very reactive due to the polar nature of the CX bond. They are very reactive due to the polar nature of the CX bond, and if we consider the polarity of the bond, then it depends upon the electronegativity of the halogen atom attached with the carbon. So according to this, the electronegativity of chlorine is greater than bromine is greater than iodine. So polarity of the bonds must be CCl bond must be more polar as compared to CBr bond as compared to Ci bond. So according to this, the reactivity order must be like this: RCl, then RBr, then Ri, but actually it is not. But in actual condition, this is not the reactivity order, and this one is the reactivity order that can be compensated on the account of the bond dissociation enthalpies of these groups. Since iodine is the best leaving group and it is largest in size in all the halogens, so Ci bond is longest and its bond dissociation energy or bond enthalpy is much lower as compared to CCl. The CCl bond enthalpy is almost about 324 kilojoule per mole, whereas for this it is about 214 something kilojoule per mole. So the difference of the bond enthalpies that make it more reactive towards nucleophilic substitution reactions. Now let us see the substitution reactions that alkyl halides undergo in one complete shot. So if we consider a alkyl halide like this, Rx, so simply if we treat Rx on treatment with aqueous KOH or NaOH, or if it treated with water, then this halogen will be replaced by the hydroxyl group and alcohol will be formed. Then we are going to have a compound like this, which is alcohol. So alkyl halides react with aqueous KOH or aqueous NOH, or if we treat them with H2O, we are going to get alcohols. ROH will be formed. If the alkyl halide is treated with sodium alkoxide, if the alkyl halide is treated with sodium alkoxide, that is R-ONA, then we will have R O R dash, that is ethers. So on treatment with sodium alkoxide, alkyl halides will get converted into ethers. If we treat alkyl halide with ammonia NH3, then primary amine will be formed. Then primary amine will be formed. If we treat alkyl halide with a primary amine like R dash NH2, then secondary amine will be formed. Then secondary amine will be formed. If we treat this with a secondary amine, then a tertiary amine will be formed. Then tertiary amine will be formed. If alkyl halides are treated with alcoholic KCN, if alkyl halides are treated with alcoholic KCN, then cyanides will be formed. then cyanide or nitrile, or we can say cyanide will be formed if we treat alkyl halide with AgCN. Then isonitrile or isocyanide will be formed. Isonitrile, or we can say this is as isocyanide will be formed if it is treated with KNO2. Then nitrite will be formed. Then nitrite will be formed on treatment with AgNO2. On treatment with AgNO2, nitroalkane will be formed, that is going to form RNO2, that is nitroalkane. Nitroalkane will be formed. So these are some of the nucleophilic substitution reactions that alkyl halides undergo, and all these products are formed. So we can learn it in a single shot, that what are the general nucleophilic substitution reactions that alkyl halides are undergoing to perform. That's all for the day. Thanks a lot for watching my channel.